Yeah. So we're gonna start with a series of relatively, I think, maybe tricky mechanism problems that cover some material from in the range of exam one and exam two, and so this should steps in here should feel familiar from alkyl chemistry. And also in the second problem, we have some protecting group chemistry, but a lot of the things we talk about the addition of weak nucleophiles or nucleophiles that add reversibly into carbonyls, and the chemistry of enolates. So I'm going to give you some time to work on these problems, and then we're going to come back and we're going to talk about them and move on to some, I think we have synthesis problems next. Okay, so let's take some time to work on this, and then we'll be back. Okay, how are we feeling? Would we like a little more time, like 5 more minutes, or we can go over them now? You can vote on this if you open up the participants window. If we want 5 more minutes, press the yes button. If we want to go over it now, press the no button. Okay, it seems like people want to go over it now, so let's do that. And then unclick it. And we'll get going. Okay, so the first problem. Does anyone have any suggestions on how they are on what they think is happening here? Yeah. So when you see this group here with the silyl ether and the triflate, this should be an instant signpost for the formation of benzyne. And so if we recall how we can form benzyne in the presence of fluoride salts, a fluoride anion can attack silicon. This makes a pentavalent silicate intermediate. Oops, lowercase. And this can collapse and eject our triflate, which is a great leaving group, to give us benzyne. And I think what is really important to remember about benzyne is that we can draw it in a couple of resonance forms. So not only can we think about benzyne in this classical resonance form here, but we can also think about it in a charge separated form. We pull electrons like this. As a vinyl anion and vinyl cation, or I guess aromatic cation, aromatic anion here, which means that benzyne has both nucleophilic and electrophilic character. And so in this reaction, it's going to be doing both. And so there, like I said, this has nucleophilic and electrophilic character. So we need to generate a nucleophile to react with it. And so we can do that from our diketonate here, or ketoester. This can also be protonated by fluoride. This proton here is very acidic. And that'll give us an enolate. It's also possible that this reaction could go through without formation of the enolate and go through the enol tautomer of the ketoester, but either is fine. We know that enolates are nucleophilic at the alpha position. And so if we push electrons like this, we can attack the cation of benzyne. And so that would get us to an intermediate that looks like that looks like this. Now this anion is very nucleophilic, and so it can attack an electrophile, which between the carbonyl, between the ketone and the ester, we'll recall that ketones are more electrophilic than esters. And so nucleophile will attack the ketone. That will make a product that looks like so. This is going to go 1, 2, 3, 4-membered ring. Oh no. For some reason my eraser is not working. Okay, so we're gonna redraw this. And now we have this strained 4-membered ring that can be relieved through a fragmentation pathway. So we'll reform the carbon-oxygen double bond, and we'll break this strained carbon-carbon bond, and we can push electrons up to the ester. And that will get us to the enolate version of our product, which can protonate. That is, of course, that looks like. Oops. And upon protonation, it can get us to our product. Any questions on this one? It can be HF. Oh yeah, I did. It can be HF that we generate. It could be, we also generate some amount of trivolic acid in this reaction. It could also just be the workup. So Tyler asks, is it reasonable to skip the formation of the formulated ring and break the CC bond in a concerted step instead of putting the negative charge on ketone oxygen, put the negative charge on ester? That's interesting. I think it's likely less reasonable than the formation of a tetrahedral intermediate that then does this fragmentation pathway. We know that in many cases for the addition of nucleophiles into carbonyls, the tetrahedral intermediate is a defined intermediate that can be trapped out and exists in many cases. So I would expect that this pathway also goes through the formation of that tetrahedral intermediate. Okay, any more questions on this one? I can't erase anything, so I'm going to stop sharing my screen for 1 second so I can restart the PowerPoint presentation. Okay, and we'll share it again. Okay. So I think this next one is one of my I think a great mechanism problem, but it is pretty challenging to see how these two building blocks come together under these acidic aqueous positions. So what I want to dig into here a little bit is what I think are some really or the way I would think about doing this problem, and go through my thinking in terms of problem solving. And so the first thing I'm going to do when I have a problem like this that's pretty complex and I don't really know how everything lines up is I'm going to obviously map the starting material onto the product. And one of the key ways I always think about doing this is look for signposts, right? Look for things that I don't think are going to change over the course of the reaction and use them to let me know where things map on and where things end up. And so I think really key to that in this problem is this methyl group here. I see that methyl group is distal from any functional groups. It's unlikely to do any reactions here because it's not activated in any way. And I see a methyl group just like it in the product. And so by mapping on these methyl groups, I get a really good sense of how the bond connectivity is going to come together. And I can map everything on to this idea of some kind of thing I can hold on to from starting material to product and give me a good sense of what's happening. And so I'll label the carbon connected to the methyl group as 1. And then I'll just go through. First, we have 1, 2, 3, 4, 5, 6. And we'll do this chain of 7, 8, 9. Make nitrogen 10. And then everything in here will be 11, 12, 13, 14, 15, and 16. Okay, so now I have methyl group 1. And so this is 1. And so these two carbons here have to be 2 or 6. And so what I'll recognize is that at position 5, I had a ketone or a ketone equivalent, right? The acetal under these conditions is likely going to become a ketone, right? And so I know there's a functional group on this on this carbon. So I think also there should be a functional group in the product. And so if I think about it that way, then this should be 6, and this should be 2, or it should be 5. Sorry, 5. This carbon here should be 5, and this should be 6. And if this is 5 and 6, then this must be 4, and this must be 3, and this must be 2. And that makes sense further because we know that we have a nitrogen atom in the starting material that could be connected at 7, 8, 9, and nitrogen's 10. Okay, and so I know what has to happen here is at some point I have to make a bond between the nitrogen of 10 and the carbon and carbon 5, right? And that is reasonable to us because we know amines react readily with ketones. Okay, and so that means we have to map on the other stuff. And so the amide of the ketone here likely, or the carbon of the amide in this product is likely not going to change also over the course of this reaction. And so it's likely as well that this 16 with the amide is also 16 in the product. And that would lead us to say that this is 15, 14, 13, 12, and this must be 11. And so we know that we need to make a bond between 11 and 3. And that also means we need to make a bond between 5 and 13. So those are all the things I'm thinking about when I and looking at this problem. And now that I have all the bonds, I know what all the bonds I have to make are, I can get a good sense of what reaction needs to happen. And so let's start with this left fragment. Under acidic aqueous conditions, the acetal cleavage will happen quite readily. This is going to happen through the protonation of one of the oxygens on the ketal. The nitrogen is also probably protonated, but it's going to be in some sort of equilibrium. Now oxygen can come down and open our acetal. This will get us in a reversible fashion to something that looks like this oxocarbenium ion. Now, it's possible here that water could come and displace this oxocarbenium ion, but it's also possible, and just as likely, that the nucleophile we have on the molecule will do so. And so nitrogen can attack here in a reversible fashion. This generates the 6-membered ring we see in our product. Oops. Plus. We're going to shuffle a proton now. So this is going to be a proton transfer step. I'm going to erase positive charge, and we're going to move it to oxygen to activate it as a leaving group. Now kick it out. Okay, so that should be very familiar to you. You should know how to do this type of reversible displacement of electrophiles from carbonyls and an amine condensation. And if that's not familiar to you, I recommend it's something you practice. Okay. So what I'll note that we've done here is formed this 10⁵ carbon or nitrogen bond. Now we'll note we're an oxidation level up from where we want to be eventually, but this isn't necessarily a problem. And so now we have this enamid shown here. And so you could, with these structures, you could think about another tautomer, especially under acidic conditions. And so if you think about this, naming here, this exists as an equilibrium structure with this, and now this can be attacked by water. In a reversible fashion. we'll now want to do another proton transfer step. So I'm not going to draw it out in its entirety, but remember we're doing a proton transfer here. And on an exam, I would want you to draw that out. You can just write PT over the arrow for proton transfer. I'm just doing it here abbreviated given our time constraints. And then from this species, nitrogen is now a more activated leaving group. We can kick out the amide to get us to another oxocarbenium species. And this exists in a series of tautomers, but we're going to examine this one first. And so why did I pick this tautomer first? Well, if we look at what we have to do, we recognize that from this structure, both carbon 11 and carbon 13 could be activated, right? We know the positions next to carbonyls are activated positions and and can be made into nucleophiles, right? And so the two things we have to do is form a bond between carbon 11 and carbon 3, and carbon 13 and carbon 5. And so we'll start by forming a bond between carbon 11 and carbon 3. And so that would look like this. This will do a 1,4 addition into our imine. And that gives us a product that looks like, we'll draw a flat still. And now we've made the crucial carbon 11 carbon 3 bond. One, two, three. Okay. And so now, like I said before, we've made this 11 and 3 bond, and the next one we want to make is 5 and 13. And now in these tautomers, neither of these forms are activated, but we know that the other tautomers can exist and exist in a series of equilibrium. And so I'm going to now draw the other tautomers. So you can imagine a keto-enol tautomerization. It's a movement of a proton from ketone to enol form. This now activates carbon 13 as a nucleophile. And you can imagine an imine-enamine tautomerization, just moving a proton that now activates carbon 5 for nucleophilic addition as an electrophile. So now we can attack carbon 5. And that gets us to essentially the core of this molecule minus this last ring. And so we can draw this flat, and then we'll draw in 2D. So and now if I draw this structure in 2 dimensions or in 3 dimensions, it is we can recognize that it's 3 6-membered rings, so that's 3 chairs, and looks a lot like our product. Oops. And now the amide can cyclize onto the ketone. This would be activated by acid first. And after another condensation step, we get to our product. Any questions here? This one, I think, topologically is pretty tricky. And so I do recommend the strategy of labeling all the carbons and noting which ones form together to make the final product. Yeah, so Tyler, that's a reasonable mechanism. It's given, especially given a lack of experimental evidence, that's certainly a valid mechanism. We know in this case that it does go through the open chain form because they isolated some intermediates, and one of the byproducts I see if they don't leave it long enough is this open chain form here. But given that, not knowing that experimental detail, I think that is a perfectly valid mechanism too. Okay. If there's no more questions on this is, remember the emphasis here was on reversible additions. And so if if we look at some of the name reactions we did here, we did this 1,4 addition here of this enol is a Michael addition. And then the addition of the enol into the imine electrophile is a Monic type reaction. And we had some other reversible nucleophile attacks in here. And so this is, stuff you should be familiar with from aldol chemistry, right? All this carbonyl-carbonyl reaction chemistry. And so I do recommend, if this problem was particularly challenging to you, really brushing up on your aldol chemistry. And now we have what I think should be some quicker problems. So these are, fill in the box problems, as well as predict the stereochemical outcome and a little bit of a synthesis problem. So we'll take a little bit less time to go through these, but why don't we take a little bit of time to do that, and then we'll discuss the answers. It's probably a little harder than what you'd, sorry, someone in the chat asked, would that type of question be reasonable on the final? It's probably a little tougher than what you'd expect on the final, but I don't think it has any chemistry that's out of bounds. And so if someone were to write a particularly challenging exam, I think it would be a pretty valid question. Okay, so that was a lot less time, but we can start going through these because I think, and if you're not done, you can keep working, obviously. But I think we should get moving a little bit so there's plenty of time for the Q&A. So does anyone have a suggestion for what the product here could be for the first one? And also, what type of reaction is this? Yeah, it's an SNAR reaction. And so in SNAR, we're thinking about replacing a leaving group on an aromatic ring. Specifically, what's good in SNR for leaving groups are you should really think fluorides and chlorides, and they're particularly good leaving groups in SNAR chemistry if they're positioned ortho or para from an electron withdrawing group. As to why, we'll remember that the key resonance forms in the SNAR reaction, if a nucleophile attacks this, we have buildup of negative charge in what is known as the Meisenheimer complex. We have buildup of negative charge ortho or para to the leaving group, and we can see that by resonance we can push electrons into the nitro group, and so groups para or ortho, electron withdrawing groups para or ortho to our leaving group is going to really stabilize this intermediate and allow for facile reaction. And so in this case, first thing that's going to happen is substitution. Of one of the fluorides, and then we get to an intermediate that would look like this after the substitution reaction, and then the other fluoride would be substituted, and so that will give us a product. Looks like this. Okay, so this should be, I think that when this problem is fairly straightforward if you recall SNAR chemistry. And so this is what I would term as a recall problem, right? So remember SNAR, and you'll be fine with this type of problem. And so, this was another thing that was heavily featured on midterm 2 is not only nucleophilic aromatic substitution, but electrophilic aromatic substitution, which kind of gets to some of the things in the second problem, which is shown here as a synthesis problem. Does anyone have an answer for the second problem? Yeah, so someone asked a great question, which is, Sarah is wondering, when the first fluoride is substituted, then the ring would not be that electron poor anymore. Is it still active enough to undergo the second SNAR? With two nitro groups, it is likely still enough stabilization of that Meisenheimer intermediate. And also you have a sort of torquing, like an acceleration of what might even be a slow reaction by the fact that it's intramolecular. So the second one being intramolecular is certainly going to help push this process all the way forward. And so I do think that it's still probably electron poor enough to stabilize the Meisenheimer complex, but secondly, it's intramolecular, so that's also helpful. Okay, so does anyone have a suggestion for the second one? estimation. Yeah, and so some people are offering some interesting suggestions here. Yeah. What I when I see this, especially this quaternary carbon here, what I think about is Friedel-Crafts acylation or alkylation reaction from perhaps a substrate. We can take this back to a substrate that looks like right? So we remember that in the presence of really strong acid, like sulfuric acid, we can ionize tertiary alcohols. So this forms a carbocation, which is then trapped by the aromatic ring, right? And so this is like a Friedel-Crafts reaction. And so I think that would be a good way to form this carbon-carbon bond. And so that's what I was thinking on this one. And so how would I make this intermediate? Well, I could say, for example, we recognize this is 1, 2, 1, 2, 3. Sorry, did I add a carbon? I did. We can form a carbon-carbon bond here through ionization of the alcohol. And so I would bring this back to a building block that looks like I think, and at this point, I think there are quite a couple things you could do. Does anyone have a suggestion for how you could get from this ester to the tertiary alcohol? Yeah, so two additions of methyl magnesium bromide would certainly do the job here. And so I think we can make this a couple ways. I think, for example, I could take an alkyl bromide and react it with this ester in the presence of a palladium 0 source. What is it, palladium? Triphenylphosphine, tetricus. The base. And that would get us to a product that looks like this. And then hydrogenation could take us to here. I think there's other ways to build in that block, but I think that's reasonable. Can anyone tell me what the name of this reaction is? It's not a Suzuki reaction, it's a Heck reaction. So yeah, the Heck reaction is the cross-coupling of aryl halides with alkenes. And so this is a Heck reaction. And so I think a reasonable sequence here could be bromination. This ended up being a little long, but it's fine. Then Heck reaction. I'm just going to put in Heck here. You can see below. hydrogenation, Grignard addition, then acid. I think there's some other possibilities here, but I think that's certainly workable synthesis. Any questions on this one? Could we add the whole tertiary alcohol part by the Heck reaction? And so I assume by that you mean add in an alkene that looks like this. This would be tricky. And the reason for that is at the, we will recall that the bond forming step in the Heck reaction, so the first step is an oxidative addition to form palladium-2, issues with our aryl group and our bromide, and that coordinates the alkene. And you can think of this next step as migratory insertion, which could give us one of two products. The aryl group can form this CC bond or this CC bond, and palladium goes on the other. So that gives us two isomers. One here, and one here. And we don't have a good way to discriminate between these two. And so it would, like you said, be unselective. The Heck reactions into alpha beta unsaturated esters or ketones is very selective for delivering our aryl group to the terminal position. And so when we use a more polarized alkene like this, we get very high degrees of selectivity. And so that would be preferred. Any other questions? Well, if we use another coupling reaction? Yeah, I think there's a bunch of coupling reactions that you could use here. If you put a tin on the edge of this, does anyone know what, does anyone recall what coupling reaction that is? Stille. So I think Stille reaction would be good too. You could also couple it to something that looks like, if you protected the alcohol, you could make the vinyl Grignard. This would be a good coupling partner, and that would be a Kumada coupling. So I think there's a lot of options there. Okay, so let's move on to the next one. So this is another SNAR problem. Does anyone have a suggestion as to which of the two halides would be displaced? The chloride or the fluoride? Can we safely assume that sulfuric acid will rearomatize the ring? Yeah, absolutely. The driving force for restoring aromaticity is very large. And yeah, so in this SNR question, we have a methoxide nucleophile. It's going to displace one of these two halides. Fluoride is the better leaving group in SNAR chemistry. However, in this case, we have a heteroaromatic ring, specifically one of the electron deficient heteroaromatic rings. And so the negative charge in the Meisenheimer complex, can be, I'm going to abbreviate the aromatic system here, can be delocalized onto nitrogen, which has the effect of essentially being an electron withdrawing group within the ring. And so the chloride here is going to get displaced faster because it belongs to a more electron deficient heterocycle. Does anyone recall the name of this heterocycle? So I see a pyridine in the chat, and I also see isoquinoline. So this is pyridine. Just one aromatic ring is pyridine. Someone says hydroxychloroquine, which is funny. Quinoline, I can check this right after because I always confuse this. I believe this is quinoline. And if that's quinoline, then what we have here is isoquinoline. Isoquinoline. Okay, so I would review, we learned the reactions of both electron-rich and electron-deficient heterocycles. We learned that after the electrophilic aromatic substitution chapter, and so I would really reorient yourself with the reactivity of heterocycles. But yeah, so pyridine, quinoline, and isoquinoline, and these are our electron-deficient heterocycles. Okay, any questions on this one? If not, we will move forward to this one on the right. There's two questions in here. Is there a difference in reactivity between chloride and fluoride as leaving group in SNAR in general? Yeah, so fluoride is a better leaving group, or perhaps is a better electrophile is what I'll say, than chloride in these reactions. So given if both Meisenheimer complexes are equally stabilized, then fluoride will react first. In this case, the chloride had more stabilization and therefore reacted first because it belonged to a more electron deficient ring. But in general, fluoride would react first. Okay, does anyone have an idea of how we could make this piece from this allylic alcohol? Cross coupling might be okay, but I was thinking of other reactions we learned. Yeah, I like oxidation, and so what's a way we could oxidize this alcohol to an aldehyde? PCC, fine. So pyridinium chlorochromate, called PCC, is a good reagent for the conversions of alcohols into aldehydes. And now we'll see 1, 2, 3. We have 3 carbons. And we want to add some more. And I saw a suggestion for vitig olefination in the chat, but I think that the beta-olefenation here would be problematic for the formation of cis-trans isomers. And so what we'll do instead is Horner-Wadsworth-Emmons, or HWE, olefenation, which is highly selective for the formation of trans alkenes. And so you react the phosphonate ester with sodium hydride in the presence of our aldehyde. We get the corresponding olefenation product as a trans-configured alkene. And now, how could we get this ester to our product? Yep. And so we can reduce esters to alcohols using lithium aluminum hydride. So recall, hydride reductions, probably the very first thing we learned in this course. Hydride reductions of esters can bring them all the way down to the alcohol oxidation level, and then reaction with TBS chloride and triethylamine, or sodium hydride and TBS chloride. We'll say that one instead. We'll say sodium hydride. Will protect our alcohol as the silyl ether. So please also recall protecting group chemistry. Can get us to here. Okay. And now this will undergo a Diels-Alder cycloaddition reaction. And so we'll call the Diels-Alder and all pericyclic reactions from the exam from midterm 3 material. So this is our diene-aphile, and this is our diene. So if we look at how our diene is polarized, we can see we can dump electrons all the way to this terminal position, and so this is delta minus. We can accept electrons into our ester and ketone for our diene-aphile, so this is delta plus. So that's the two sides we're going to arrange in our Diels-Alder reaction. Now I'm going to draw the diene here in the S-trans or S-cis configuration, which will, in perspective, look like this. This should be very familiar to us by now. And this will react with our alpha beta tetrated ester. Like so. The endo-exoselectivity here is a little bit tricky for us to think about because both the ester and the ketone could accept electrons as part of could accept electrons in an endo configuration. And so in this case, I've gone with the group that's smaller as our endo acceptor, and we'll see what outcome that gets us to. And so the product here would then, from our transition state, look something like this. And so we'll see that the hydrogen groups here are on the same side as the 5-membered ring, and on the opposite side, the benzyl group. And so we'll get a product that looks like which I think is, yeah. Any questions on this? Eric, I don't quite understand your question. Tyler, if we use LH in our synthesis, should we be scared of reduction of the benzylic position? Oftentimes, no. So the benzyl group is rather hard to remove with lithium aluminum hydride. You want to use something like hydrogen on palladium instead. And so this is pretty robust against the benzyl protecting group is pretty robust against lithium aluminum hydride reductions. Certainly, you'd be able to control over the reduction of the ester in its place. Yeah, so Caitlin, you asked a great question there. Really, in this case, both are endo products, I guess you could say, because they both have groups that can accept electrons. In this case, I've decided to put the smaller of the two groups under the transition state because it can still accept electrons, and it's less hindered than the 5-membered ring. But I think you could have had a reasonable shot going the other way. It was just a practice in drawing stereochemistry here. Because both groups are endo acceptors. Okay, so let us move on to this synthesis problem. And what I have actually on the next few pages are practice problems that a friend of mine made for this class a couple of years ago. And looking at the time, we're definitely not going to get through all of them and still be able to do the Q&A. So what I'm going to do, we'll probably do this as the last one, do the Q&A, and then I'll post this practice worksheet plus all the answers onto the box for you guys to have extra practice. And so we'll tackle this kind of challenging problem, and then you'll have lots of practice to do afterwards, and we'll still have time for Q&A then. And so take a little bit of time to work on this, and then we'll do the Q&A. Okay, so that's been a very short amount of time, but let's walk through this together as we can think about some of the synthesis involved in this problem. And then, like I said, I'll post this whole worksheet to the box for you to do extra practice, and we can get to the Q&A. So when I look at this molecule, um, first, I think there's a couple of key recognitions for us to pick out. And yeah, a couple key recognitions for us to take out. A is the hint that the synthesis includes a Robinson annulation step. And so I'll remind you all of the Robinson annulation and of the building blocks we have here. We have A, B, C, and D. And so we can recognize that we can combine A and D together through Robinson annulation. That's going to build a very crucial part of this molecule. So if we look at that, plus, remember that the Robinson annulation first involves the formation of an enolate here, and then a Michael addition of that enolate into this alpha beta unsaturated ketone, and then the aldol condensation from this position onto one of the ketones. And so please refamiliarize yourself with the Robinson annulation. It's a very important reaction. So we can just catalyze it with base here. And that can give us products that look like this. Okay, so that was the Robinson annulation step. If that is confusing to you, if you have trouble with that, please look up the Robinson annulation. Very important reaction. And so when I look at this 6,6 system with this methyl group here, I can recognize that it maps on very well to this portion of the molecule. And so now I'm wondering, how do I construct the other portions, like this upper 6,5 fuse system? And I can recognize that I can probably add this vinyl group here using methyl magnesium bromide, or perhaps another method. So next we want to tackle how we think we can make this 6,5 fused system. And I think in synthesis, a huge flashing red light should be the formation, or if your target contains a 6-membered ring with an alkene in it, it is very possible that you could make this through a Diels-Alder reaction. Right? So tactically, when you see 6-membered rings with an alkene in it, you should think that probably came from a Diels-Alder reaction. I can make that using a Diels-Alder reaction. And so the two pieces here then would look something like a diene like this. Oops. Diene like this. Sorry for drawing over the words. And we might have to do something to this bottom half, like a protection or some other way to make it unreactive. And then we could react this with a dienophile like so. to form the 6,5 fuse system. And we recognize that this could be formed from the intramolecular aldol condensation of this molecule. So if you envisioned forming an enolate at this position selectively, you could form the 5-membered ring. That would eventually give you this product. So you could get to here, I think, just under thermodynamic enolate formation conditions, you could get to this building block. Okay, so we want to get to something that looks like this, couple it to that. That I think should make sense to us. And so how can we do that in a pretty selective manner? Let's see. So I think the best way to do this would be, or I guess what I'll say is we have some challenges here, right? Being the 2 carbonyls. And so we might want to selectively protect and deal with each of them separately. And so ketones are more electrophilic than alpha beta unsaturated ketones. So when we react this, we can protect this as an acetal. It'll selectively protect the ketone. Now I've done this so that we can essentially deal with these 2 groups separately. I think there are some shorter answers that you could come to that would avoid this step, but would be less selective ultimately. So I'm just going to propose the most selective synthesis. And then what I'll do is form the vinyl triflate from this here. So we can say LDA and def2do. This gets us to a substrate that looks like this. And now what we have here is this very hindered diene that I think would be pretty unreactive. Also given the fact that it has an relatively electron withdrawing group on it. Okay, and so now I'm going to cleave the acetal under acid and water conditions. Like I said, I think there's a shorter way to do this that is less selective that we can think about a bit. That reveals our ketone. Now I'm going to add a vinyl group in using methyl magnesium, vinyl magnesium bromide. And now elimination of this alcohol, which we can do with acid. Can get us to a diene that can react with our dienifier. This and this can react together to give us the full skeleton here. like I said, I think this diene would react more readily than this diene because this diene down here is so hindered and has, is very, very hindered. And so would be unlikely to react. Now, then you could do a commodic coupling. Or perhaps any kind of cross coupling here. Perhaps not a commodic coupling, but a Stille coupling would be better. To give the product big A. Yeah, so I think this might be this is a pretty steppy synthesis, and I didn't give you a lot of time for it, so definitely don't be alarmed if you couldn't get to it. But I think the key takeaway here is when you see these 6-membered rings with an alkene in it, you should think Diels-Alder reaction. So someone asked, why are ketones more reactive than alpha beta unsaturated ketones? If you think about the positive charge, if you think about these resonance structures for a ketone, and then also for an alpha beta unsaturated ketone, don't know why I'm doing this all at the top of the screen. That positive charge has another resonance structure that delocalizes it over 3 positions. And we know that delocalization is a stabilizing effect. And so the more stable cation is less electrophilic. And so that's why alpha beta unsaturated ketones are less electrophilic than ketones. Is the removal of the alcohol selective for that diene as opposed to the S trans? So remember that S cis and S trans dienes can equilibrate just by a rotation. And so the selectivity in that way doesn't matter, and it's always going to eliminate in the endocyclic position. Yeah. Remember that this bond can rotate. Well, so the only possible off positions here, Tyler, are these, and that's always going to give the endocyclic cis alkene because trans alkenes and 6-membered rings are too high in energy. So it's always going to be this cis alkene here. Could we add vinyl magnesium bromide to the carbonyl on the left instead of LDA and dehydrate that to form the diene? Yeah, so I think that is the shorter but less selective answer. You would envision adding vinyl magnesium bromide to both carbonyls, and then upon elimination, you have 2 dienes that can compete in the Diels-Alder with each other. And so I think that would be problematic. Yeah, that's a good question. Whether or not the Grignard could react with a triflate group. I think if you had too much of an excess, it might for sure. But I think in most cases, the trifle group will be relatively stable to Grignard conditions. Yeah, I think it should be fine. Okay, so that's all we're going to do in terms of practice problems for tonight. I have a lot more in this from this worksheet, so I will definitely post this worksheet onto the box. Let's find it like a blankish. I should have put in a blank page. So what I'll do is I'll stop sharing this. I will share now just a whiteboard. So if you have any questions, feel free to ask. I'll hang around until people don't feel like asking questions anymore. Oh, do you mean lab exam? I don't. So Pete was covering the lab exam stuff, so I'm not entirely sure how he wants to handle regrade requests. I don't know when his next office hours is. Maybe you can ask him then. And if you can't get a hold of him, I can run it up the ladder to him. Yeah, so the timing for the final will be announced by Felix soon. What I'll say is it's going to be next Thursday, and it'll be very similar to last exam. Will there be a practice final? I hope so. It depends on, as all things do, the content of the final itself. Then we can release practice material once we have it finished. I will release these practice problems for you to look at in the meantime, but then hopefully when me and Felix pin down what we're doing for the final, we'll release a practice one. So do you mean midterm 3?
Yes, sorry.
That's fine. And for those of you that don't feel like sticking around, thank you so much for coming to my review sessions. I think we've had, of course, a difficult semester, but it's been a really nice part of my week, being able to do these review sessions still, and I hope you've all enjoyed them. It's been fun, and I wish you all the best of luck on all your finals going into next week. Can we go over question 7? Yeah, so since we have a question on question 7 on the midterm, let me share the, okay. Okay, so can we go over question on 7 on the 7th final? Specifically how to put the bottom rings, how to use the sequence ring and deals all there, but it was wrong. Yeah, so I think what a lot of people struggled with, I think, on this question in the final was order of operations, and making sure that you were able to do a very selective Diels-Alder reaction. So the best answer is what I've shown here, which forges the 6-6 membered ring through a normally matched Diels-Alder reaction with this E known as the dienophile. The reason we do this, many people took some sort of vinyl halide like this and cross-coupled it and then tried to do the Diels-Alder reaction. And I need to pick which screen I want to do. There was a lot of examples, for example, of people attempting to do Diels-Alders, or maybe not. Attempting to do Diels-Alders with substrates that look like this plus this. But here we have some real challenges with selectivity as to whether or not this is going to react as the diene and this the dienophile, or will this react as the diene and this the dienophile? Will this instead react with this alkene instead of this selectivity here is a big problem. That selectivity challenge is obviated by the use of the appropriate dienophile. But what a lot of people also did was cross-coupled beforehand. So they had the aryl group here instead of the halide, and still you would have issues arising from selectivity. And so you have to be really careful about order of operations to ensure that your answer is as selective as possible. Does that make sense, Golsa? What else do we got? Yeah, that's a great question, Julia. So why is fluoride a better leaving group in a nucleophilic and aromatic substitution than the other halides? So when we think about nucleophilic aromatic substitution, it has two steps, right? You have the addition of a nucleophile to form your Meisenheimer complex. We'll say EWGs here. And we've been kind of careless with the way we've talked about this in the class, and perhaps a better word for this is, instead of better leaving group than chloride, is a better electrophile than chloride or bromide or iodide. And so because there's two steps here. So we form the Meisenheimer complex, and then we eject our leaving group. And what's crucial is the relative rates of these steps. It turns out that the barrier for ejecting this leaving group is really low because it's tied to forming aromaticity. And so this second step is always very fast. Whereas this first step, because you're disrupting aromaticity, is very slow. And so what matters here is not the ability of F- to leave, it's the ability for the nucleophile to attack carbon, right? What's going to accelerate our slow step? F- being a good leaving group doesn't accelerate the slow step at all, right? But what does accelerate the slow step is F- being very electronegative, or the fluorine atom being very electronegative. More electronegative than chlorine, more electronegative than bromine, more electronegative than iodine. And what that means is that carbon has a higher partial positive charge at the carbon connected to fluorine relative to chlorine, bromine, or iodine. And that means that it's more electrophilic. And so this nucleophilic attack, which is the slow step, is accelerated by having such a hard electrophile like fluoride. And then the leaving group ability is kind of not important because that step is so fast. And so in this case, it's really more about the carbon connected to fluorine being a better electrophile than that connected to chlorine, bromine, or iodine. Does that answer your question? Yes, so the preference for addition into fluoride is kinetic rather than thermodynamic, and these reactions are under kinetic control because they're not reversible. Yeah. Can we go over how to determine migratory aptitudes? The Beer-Villiger reaction. Yeah. So this is thought of in a couple of ways, classically, but the basics of it can be thought of by, so in the Beer-Villiger reaction, we take ketones, and react them with perbenzoic acid of some sort to get to ester products. And so key to that is the formation of some tetrahedral intermediate that looks like this. This is normally an acid, but it's fine. And now we have to think about normally we push arrows like this, and then a group migrates, kicks out. And so how do we determine which of these two groups is going to migrate? So migratory aptitude is kind of thought of as nucleophilic character. So what I mean by that is groups that better stabilize positive charge migrate quite well, with one exception that we'll talk about in a second. And I guess a reason you could think about that is yeah, it's hard. You can think about there's like you can think about it in a cationic way or anionic way. So we'll think about the anionic one first. Let's think about this reaction in a stepwise fashion. And so I think if you erase that arrow and draw instead this first, you get some people will make an argument here that says the two possibilities are the formation of a tertiary carbanion and a secondary carbanion. The tertiary one is going to be more, and a primary one, and the tertiary one is going to be more reactive. It's more electron rich, so it's going to attack faster. So this argument says that the tertiary group is more nucleophilic than the primary group is. I think that's a reasonable argument. Let's see. There's another, so you could think about this happening also like essentially think about doing the migration first. And maybe I think I like this one better. They ultimately are saying the same thing. So if you don't start from oxygen here, and if you migrate the group first, you get well, no, that's not very helpful. Yeah, so I think people mostly just think about it as a nucleophilicity thing. Which group is more nucleophilic than the other? And the group that's more nucleophilic is the one that's more electron rich. And so the one that's more electron rich is going to migrate in this case. The other thing, the other important thing here is that what kind of throws out the rules for migratory aptitude is the migration of hydrogen atoms is very fast. This is due to their S-shaped orbital having great overlap with everything because it's just a sphere. And so hydrogen atoms migrate faster than everything else. And that's not really a function of nucleophilicity or anything else. It's a function of orbital shape and kinetics. What else? Okay, not seeing anything else. I'll give another couple seconds for someone to say something, but if not, once again, just want to reiterate, thank you all for being really good sports this semester. Given a pretty raw deal, but I think we've had some fun in these review sessions, and like I said, they've been a really good time for me, and giving me something to really think about every week. So thank you guys for always showing up and having a good discussion. It's been really fun. Ooh, one more question. When predicting a product, how do we know if the OH group stays in the product or gets eliminated? Erica, are you referring to like aldol chemistry problems or just like in general? What I'll say is generally acids, alcohols are eliminated under acidic conditions, the exception being if they're next to an electron withdrawing group or beta to an electron withdrawing group. So if we have an example like this, now through an E1CB mechanism, the alcohol can be eliminated. So I would say alcohols can be eliminated if you think they're going to be eliminated. They can be eliminated under acidic conditions and under basic conditions if beta to an electron withdrawing group. But those are the conditions I would expect to see alcohol elimination. Yeah, we can go over ISO substitution. I don't think it's that important, but we can do it for sure. So ISO attack only really occurs in like a meaningful sense for aromatic rings with silo groups. It can happen with terp-butyl groups, but tends to be less likely. And so, these are pretty electron rich. And so in a lot of situations, in a lot of situations that this would direct orthopara, but instead it directs ipso, and that's a special function of silicon and some really bulky carbon groups that stabilize positive charge. And so you can think about this reacting with an electrophile of some sort. If we consider, various positions of positions here, we could have positive charge here and the electrophile here, or the other way around. So charge here And we can go through into all of these. But what's really special about silicon in particular is what it's very well characterized as the beta silicon effect. And that's that carbocations that are beta to silicon, so alpha beta to silicon, are stabilized through are stabilized quite well through what is essentially very strong hyperconjugation. And so people will draw stabilized adducts that look like with positive charge delocalized all across this three-membered ring. And you can think about that meaning that both these bonds here are dashed essentially, as in have some amount of non-bonding character. And because of that great stabilization of this beta carbocation, the substitution of the electrophile into the ipso position is preferred. And now that we have substitution into the ipso position, the pathway will terminate through loss of the silyl-cation, and it's essentially like we eliminate a proton, but in this case we'll eliminate a pretty stable silyl-cation and get ipso substitution. So this is a function of the beta silicon effect. And so Erica asked can we assume that if there are acidic conditions or workups in the synthesis, OH groups will almost always be eliminated? No, I wouldn't make that assumption. So if there are acidic conditions in the synthesis, it could eliminate the hydroxy group. I would not imagine we would devise a question where the alcohol is eliminated on workup. I think that would probably be that wouldn't be a well-designed question. All I say is, yeah, it's only when it's next to a ketone via aldol condensation that you could expect for it to go all the way to the condensation product. That would be my thought. Cool. Yeah, I'll repeat what I said. So for lecture quizzes, we haven't 100% decided what we're going to do yet, but what we're heavily leaning towards at the moment, and will almost certainly be the answer, is that we will be giving you full credit for both the lecture quizzes that you missed. So you just get 10s out of 10s. It's not your fault that a pandemic happened. So we will be giving you credit for those quizzes. And so that's how we'll probably handle it. Anything else? Okay. Have a good night, everybody.